aspects of novozymes, viscosities, and how such things you can plan in your research. And after that, this lecture, because we have already completed a few slides of that lecture, so it will be short presentation of 15 minutes, and after that we will break for lunch, and then after that tutorial. Tutorial will be the very important session for us because we can discuss so many aspects which you can note it down and then we can discuss. I invite Dr. Howliu to start the guidelines.
Okay, let's continue our the lecture tour. I will talk about the factors limiting cellulose activity. It's claimed that cellulose plant has a very complex cell wall structure. There are a lot of barrier made of especially made of lignin. So in the first step of the biorefinery, we have to break down the cell wall. We have a lot of technologies, new technologies, especially based on the thermochemical process. Thermochemical means there is a heat. Heat means steam or pressure. We will heat up the system, and there will be chemicals to break down the cell wall components to degrade lignin or degrade the hemicellulose. After pretreatment, the cell walls, the size of the biomass will be decreased. Decreased, and the cell wall structure will be partially destroyed. Then there are enough spores and force for the attack of the enzymes into the substrate. Sometimes we also do the surface modifications, like these two pictures. After the chemical process, the surface, the lignin particles on the surface, that in dark color, will be removed. After that, all the cellulose, all the surface is covered by cellulose microfibrils. It means substrate is exposed to the enzyme. The cellulose accessibility is improved. The digestibility is also enhanced. It is very important to find a good pretreatment method. Okay, if we have soft wood, it's better we use sulfide. Sulfide is very sufficient, very efficient. Follows acidic sulfide process. If we use a corn stirrer or corn hulls as a dilute acid, pretreatment is enough. Okay. After the pretreatment, we can also see the enrichment of cellulose. The content of cellulose is higher. Although the lignin barrier can be removed from the pretreatment, we obtained a lot of spent liquor. In the spent liquor, there are derivatives, there are dissolved lignin fractions. These fractions are small particles. They can also absorb the cellulose enzyme, cause a non-productive binding inhibition. This inhibition is very important because after 24 hours, the cellulose you cannot detect long cellulose activity because of they were found on the contaminants on the lignin derivatives. Okay, the non-productive binding inhibition is mainly due to the three non-covalent forces. They characterize this as first the hydrogen bonding, then the covalent, the electrostatic force, and the hydrophobic force. They can directly detect the three kind of forces. Use AFM, use modified FMT. This team obtained very good results and has proved that the hydrophobic force is a major force between the lignin and the cellulose CBM. CBM is binding domain. We also developed a lot of new technology to reduce the non-productive cellulose inhibition. We can use some additives to block the leading particles away from the cellulose binding. The first one is surfactant. Surfactant is very efficient to reduce the surface energy to enhance the motivation of the enzyme on the surface of substrate. And the next one is the BSA. BSA is a protein, it's a pure protein, a standard protein. It can replace the cellulose protein to bind with lipids derived molecules. So release the cellulose specifically bind to cellulose substrate. And I also developed technology use chemical use salts, especially the calcium salts and the magnesium salts. This work was done in Wisconsin because the water in Wisconsin is of very high hardness. The content of calcium and magnesium is very high. I found that if I use pure water as a enzymatic hydrolysis is not good. But if I use tap water, the result is better. So I tried to explain. I found that these two salts, two metal ions, they worked out. Then I will introduce the cellulose products supplied by enzymes. The first cellulose commercial renewable is cellulose 1.5 liter, and the enzyme 188. 188 is very important. It is a beta glucosidase. The ratio of their activity should be 1 to 1.5. It's optimized ratio. And the activity is optimal under conditions of pH 5 and 50 degrees centigrade. Okay. Then another time has a product named as CTEC. In 1910, around 1910, they produced CTEC2. CTEC2 has a very high FPU, 150. Then in the year 2012, they produced CTEC3. CTEC3 is a much higher cellulose activity. In the CTEC3, there are not only cellulases, but also xylanases and other hemicellulases, and also pectinase and some esterase. I heard from the literature they have CTEC5. I don't know, but I did not see any CTEC5 product now. So this picture is from Northline website. They present that CTEC3. CTEC3 is very efficient for all of the leading dominant material, raw materials, and for all of the leading treatment technology. Because the price of CTEC2 is very high in China, 1 kilometer it sells 40 Chinese yuan for 1 kilogram liquid. We want to reduce the price of reduce the cost of enzyme, so I tried to test all the activities in CTEC2, and I made a similar one. All of the components are made in China, but they are from different species. They have different activities they combine together, including the cellulase and xylanase from Utah. Utah is also famous enzyme supplier in China. And the Shangsheng is in North China. It provides the best beta glucosidase and the best design. Best time they provide me the esterase. Esterase is very important to break down the linkage between hemicellulose and the lignin. So I use a homemade combination of in lines, I compare it with CTEC to I found okay, the activities somehow equivalent. Okay. And I also developed the additives. I use additives combined with the CTEC2 and the line. We got a very good result from silicon gas to produce ethanol. From 1 ton of material, we can produce over 400 glucose totally. Now we have to solve a lot of problems, especially the inline cost. So we have a lot of research, and this research is not from me, but from another group in my school. They do the cellulose recycling. They told me that cellulose recycling, if we can do that, we can save at least 50% of the cost. This table was provided by these authors. There are three major components in the cellulase, and the activity was tested after enzymatic hydrolysis of cellulose. About half of the activity can be retained after the process. One of my friends, Professor Low is a very famous professor in my school. He developed a new technology, used lignin. Previously, I mentioned that the lignin can bind with cellulose. He developed a new lignin derivatives. The lignin derivatives has a positive and a negative different groups. Okay, so its solubility can be adjusted by pH. Like this. At pH 4, it dissolves and binds with cellulose. At another pH, at pH 3.0, okay, it precipitates as a solid, as a particle. Then the bonded cellulose can be removed from the liquid, from the saccharides. They use this technology and to try to do the recycling of cellulose, and it's very successful. All of the major components can be recycled. Okay. And for the next round, you can adjust the pH to pH 4, and the lignin bond with cellulose can be dissolved, and the cellulose can be released from lignin. So it's a very convenient way to for cellulose recycling. My work focuses on the high solid enzymatic hydrolysis, because the first generation refinery, they do the ethanol distillation. They require the starting fermentation growth has a high ethanol content. It means we have to do the hydrolysis at high solid conditions. High solid means there's no sufficient water. If we do not have sufficient water, the biomass will absorb water, and the slurry cannot flow, and the mass transport is very poor. The inline efficiency is also lower. So I developed a new technology, is cell separation. This is a palm, the royal palm, very popular in China, in South China, royal palm. I use the leaf of the royal palm and do the sulfide cooking. Sulfide cooking is this tank. It's a KRK digester. After the cooking, I do the fiber fractionation. There are a lot of different sizes of screen. Then the parenchyma cells and the fibers can be divided, can be separated. And next I use this parenchyma cells to do the ethanol production, and use this fibers to do the fiber production. This is my results from the cell division and enzymatic hydrolysis. We can see that fibers are relatively difficult to be digested, but the parenchyma very easily to be digested. I use surfactant as an additive. Then I do the batch feed Yeah, fed batch process and the single batch process, I compare them, one the result are the same. After 120 hours, the glucose produced from the royal palm biomass are the same, over 150 gram per liter. If all of them can be converted to ethanol, the ethanol content is around 80%. We are also trying to do the ionic liquid research, ionic liquid for the cellulose dissolution. After dissolution, it looks like this. It's about transparent. There's no solid at all. All the cellulose crystal were broken down. And if we add water into the ionic liquid, all the cellulose can be deposited, but the crystallinity, there's no big crystallinity index. Then the enzyme dosage can be decreased by 90% or 95%. However, I found I cannot get a good cellulose in this system because the ionic liquid is organic salt. Many proteins precipitates because of the salt after infection. And cellulose can also be unfolded and deactivated in the ionic liquid solution. So I did not do the hydrolysis. This experiment was not successful. Some other authors work, they obtained some good results, like with John. They get a gene from a lake soil, from the saline alkaline lake soil. They use metagenomic technology. They get a gene and they express it, and they get a good result with this liquid. This is liquid. The content is 20%. It's a very good result. Okay, almost all of the cellulose activity was retained in this system. And there are two other research work. The last one, they use a PEG. PEG can modify the protein, improve its tolerance in salt solution and ionic liquid. I have some questions, and I hope we can discuss these questions this afternoon. The first question is it good to immobilize cellulose? We all know that they use immobilization. We can save the cost of amine, but can we do that? Can we immobilize cellulose? It's the first question. Another question is how can you recover cellulose from hydrolysis slurry? Previously, I should hear. This result from Professor Low, my friend. He recovered the cellulose in liquid. But how can we do that in slurry? Solid from solid. Recover the cellulose from solid. Okay. And the third question is, what's your method? What's your process? Can you design an experiment to get only liquid tolerance cellulose? Okay, I have these questions. And let's stop here. Thank you for your attention.
So, thank you, Dr. Liu. And I think we'll proceed for lunch now. And we assemble here that the lecture will start at 2:30, but we have to assemble here by 2. Okay, so that we can start something, and then we will be having the tutorials. Tutorial session is very crucial for all of us because the real discussion we can do there, and we can also compile the questions related to the topics. And I think hope you have got the study material, those who are registered to the program, so you can go through it in between. Thank you for your attention. You can announce for the